Yeah. Hello, everyone, and good evening to all of you. Welcome to this second live session of this NPTEL course, Aqueous Corrosion and Its Control. I think that you people have so far seen lectures starting with thermodynamics, then kinetics, then we looked at the uniform corrosion, then the galvanic corrosion, then we moved on to pitting corrosion, crevice corrosion, and then I suppose you have completed the intragranular cracking or intragranular corrosion, I would say. So I do hope that you people had a reasonable understanding of the subjects, both the fundamentals and as well as the, the applied oriented. The sense like we have also given examples where the galvanic corrosion occurs, where the uniform corrosion occurs, and where pitting corrosion, crevice corrosion, and even intergranular corrosion really occurs. So it's nice to see that we do have live sessions to clarify these points. We did have receive a few questions from you people. Now I think I can probably answer these things the first. Meanwhile, and those who have joined now, if you have any questions, please put them in the chat box, and the TAs will let me know what are the questions that you have in mind. Please do feel free. Don't hesitate to ask any questions. Okay, asking questions is not a problem. Okay, but not asking question is really a problem, because the whole idea is to understand this subject. So let me start with the question that we have already received. The first question is from Pravin Vengara, I suppose, right? And his questions, the first question here is, what are the key factors in selection of filler wire or consumable electrodes to avoid intragranular corrosion of wells and heat affected areas? What I understand from this and from the subsequent questions is that, Praveen, you should have a clear idea about what is this so-called heat affected zone corrosion well decay. As we have seen in these lectures, there are about, I think, 4 hours of lectures, I think, right, on sensitization. We deal with the sensitization of stainless steels. And mostly we talk about sensitization of austenitic grade stainless steels. We also talk about sensitization of ferritic stainless steels. And sometimes, very rarely, we talk about the other forms of stainless steels. So when you talk about this heat affected zone corrosion, or the corrosion of the heat affected zone of the weldments, which occur at the intergranularly, we are talking about what is called as the corrosion of the weldments with respect to stainless steels, not the steels. First point. The second point that I would like to also mention is that we talk about, when you talk about weld decay, let me just take this on the screen here. I hope you people, you can able to see this. Oops. Oh. What is going on here? Okay, let me just take this, stop presenting. I may go to the presentation again, window. Let me go to this, share it now. I hope you are able to see this window here, right? Now, when you talk about, the sensitization or weld decay, we talk about, I just sketch it here. Right. So this is a stainless steel, and so you weld it, right? You weld it somewhere here. Let's say is maybe a butt welding or something like this. Is a welding like that, right? And okay, so this is called as, weld fusion zone, right? Weld fusion zone, right? And somewhere here, very close to the, somewhat close to this, you will have what is called as weld decay, right? And on either side of it, you have weld decay here, right? This is called as the taper zone. This is called as weld decay zone. Now, it is very important to understand when you talk about heat affected zone. Heat affected zone in general for a weldment means when you heat it here, when you weld here by an arc process or some other process, okay, heat is getting transferred here, and some of these regions, or these regions, right, all these regions, I would say, there is a transformation occurs within the metal. Please look at here, it becomes a liquid, whereas here in this region, okay, doesn't become a liquid, rather the transformation occurs within the solid. Okay, some phases really occur. Okay, now when you talk about steels, for example, there is a wider region of heat affected zone where there is a change in hardness, change in phases and all. Unfortunately, we cannot discuss more in details. Comes under welding actually. But what I would like to say here is this weld decay zone is characteristics of stainless steels, mostly austenitic grade stainless steels and the ferritic grade stainless steels. In this place where you notice that there is going to be sensitization, right? Where if you're going to magnify this and see them in the microscope, they'll say you may be seeing some grain boundaries. You may have the precipitates, the chromium carbon precipitates. And surrounding this, there is a depletion of chromium here. Okay, this chromium depletion causes the attack. Okay, so the heat affected zone is essentially depends upon the composition of the metal. Whatever you weld here, okay, this composition has no role to play. If I choose a different filler wire here, you may choose, the corrosion of this zone may change, but corrosion of this will not change. The corrosion of this would depend on the thermal cycles. Like, for example, what is the temperature? What is the time taken here, right? What is the temperature this zone has reached? How long this zone remained in that particular temperature? So it is essentially depends upon the temperature experienced by this zone due to welding and the composition of this zone. What is the composition of this? What is the composition of this in stainless steel? For example, you may have iron, you may have 18 chromium, for example, you may have 8 nickel, okay, or you may have as a 0.08 carbon. In this case, there's sensitization, but you're going to change from here to, let's say, iron, 18 chromium, 8 nickel, and you're going to take, let's say, 0.03 carbon. Now what happens? Now sensitization does not take place, irrespective of what is the filler wire used here, as long as the thermal cycle remains the same here. So the heat affected zone area, so-called heat affected zone here, we call a weld decay zone area. The way it is corroding is independent of what is the filler wire that you choose here, what consumer is going to use here actually. Of course, if you're going to choose a consumable that leads to change in thermal cycle, it's a different story altogether. So it is independent of this. Of course, when you talk about choosing a filler wire, there are also regulations, there are guidelines what filler wire to choose. For example, you're going to use 304L, and you're going to use a 304L filler wire. You are going to use 316L base metal. You're going to use 316L filler wire or electrode, right? But of course, the 316L electrode will have a slightly different composition as that of this. So to derive the point, whatever happens here in terms of composition, there's no role to play here. So that is what no role to play here in terms of weld decay. So that's a point that I wanted to say. I hope this point is clear, but if the person has some doubt, please do let me know. I know I just want to respond to it. Are you clear about it? Is Pravin there in the meeting? Okay, so I hope that this is understood now. Let me now go to the next point. Next point is the question reads like this: I experienced a A106 CS pipe welded with ER70S3. After 1 year service, weld area corroded from inside. Almost 70% of the weld metal is gone and now looks like a groove. Is it a galvanic corrosion? What would be the cause? We expect untreated seawater is passed through the line, even though why exactly the weld metal only is washed? So this is a question. So the question, if I summarize here, that this is a carbon steel, it has been welded, it's a pipe actually. Now along the same weld, along the weld actually, the corrosion really is occurred. It is occurred, okay? Suppose this is the sheet and there is welding here, the attack has taken place along this, okay? And please notice this is a carbon steel actually, okay? And it is not a stainless steel. So if it's not a carbon steel, of course, we are not going to talk about weld decay. We may still talk about heat affected zone, but the heat affected zone generally is not a problem in the low carbon steels actually. You know, if the strength is low, it's not going to matter much. Now the corrosion has occurred here. Obviously, there is a problem here. Why it can happen? It may happen for so many reasons. The one simple reason could be that the composition of this filler wire may be relatively anodic in nature. Suppose we talk about galvanic corrosion, right? Suppose assume that this filler wire, what electrode that it choose, is relatively anodic compared to this, then that can happen. But in the carbon steel, it's very unlikely you see a huge difference in the galvanic corrosion. But of course, if there is a problem here, then you can add a little bit of nickel is possibility to make it noble. But there can be other problems unless otherwise you are sure about it. What can be a problem? Maybe you are not, the welding is not done properly. There is improper fusion has happened. You know, that is one possibility that takes place. There is another possibility can happen is that if it is seawater that you are having it, there can be a microbial corrosion taking place. Especially the microbes, they settle normally along this region because it's a rough surface, the microbes generally settle on this. But all this you need to analyze and exclude the possibilities. Okay, so there is a possibility of, yes, the filler wire relatively anodic compared to the base metal. Yes, there is a possibility of a galvanic corrosion because of that. Yes, there is a possibility of improper fusion that has happened that led to corrosion of this actually. Corrosion, wear and tear all can happen. Yes, there is a possibility of what is called as microbial corrosion taking place. So all these possibilities one can examine by taking a cut piece of this actually and try to examine for various in all this part of it actually, so that you get a clear idea why it is really happening. Okay, one of the problem that happens in the case of weldment is once the groove is formed, when there's a flowing, there's a turbulent flow, and so there will be more kind of corrosion takes place. It's also possible it can happen. And I don't know the velocity of this thing. What is the linear velocity? The linear velocity is larger, then of course there is erosion corrosion. Carbon steels are not meant to be application seawater for high velocity. If the velocity is more than 1 meter per second, I think the carbon steel may have problems. So you need to look at what is the linear velocity. I'm not talking about volume per minute and all. I'm talking about the linear velocity to which the water is sent there. I hope this point is clear. If it's not, if you still have a problem, please do let me know. I can clarify this further. Okay. Let me, is that fine? Okay, so I assume that is clarified. Let me move on to the next question. It's a very interesting question again here, right? The question is, it reads as follows. Zinc is not recommended for carbon steel surface as a coating at high temperatures service in corrosion aspect. Very, very well taken, right? That's what I also mentioned when you talk about the galvanic corrosion, because zinc starts passivating at high temperatures above 80 degrees Celsius, right? And zinc becomes noble and steel becomes active. So there's a galvanic reversal taking place, right? Now, is it okay if we apply another paint coating over zinc to protect it from atmospheric oxygen at elevated temperatures? Right? I found zinc-rich epoxy is applied as a primer on carbon steel surface, which is operating at temperature above 100 degrees Celsius. But it have another one or two coatings with non-zinc paint coatings. Very interesting question. A very interesting problem. Okay. Now let me try to analyze this problem more scientifically and see what we can do. Right? Yes, we know that zinc coating is not good when the surface temperature exceeds 80 degrees Celsius, and you can't apply it on steel surfaces. Galvanic reversal, fine. Now what? Now let's go to the applying a paint over zinc, right? Now people apply paint over zinc in order to increase the corrosion resistance. Okay. Then what is the purpose of zinc? The purpose of zinc is, should the paint coating fail, the zinc coating should protect the steel surface by sacrificial action. That is the whole purpose of applying zinc coating on the metal surface. Now assume now the case where the paint coating has gone away because of some reason, maybe mechanical damage, whatever it is. Now zinc coating is exposed. Now, should the zinc coating prevent galvanic corrosion through sacrificial action? No. It is going to act same way it would act had the steel been coated with plain zinc. So zinc is not going to help at all once the paint coating is gone. Similarly, I do have a serious reservation in terms of zinc-rich epoxy painting. See, there are also, that is called zinc silicate. See, there is one more coating called zinc silicate coating. Please look at zinc silicate coatings are different. Zinc silicate coatings, they prevent corrosion in a different manner, whereas zinc-rich organic paint coatings work in a different manner. Okay, the zinc silicate coatings, they offer protection by, by the mechanism is a very hard coating, right? It prevents corrosion on this actually. Okay, so I doubt that this zinc would have really good benefit. You may have a minor benefit. I do not see really big benefit by having this at all. The one way, of course, to ensure is see that it is being it is being tested. You can look at this actually, can be done in a laboratory, get them clarified. But prima facie, I could see that this is not going to help much actually. That's my answer for that particular question. Let me go on to the last questions asked by him. Okay, that is how corrosion, that is within bracket intragranular, takes place inside the metal without the presence of electrolyte, right? We say intergranular corrosion. See, intergranular corrosion. Look at this corrosion, right? The corrosion occurs because of the presence of the electrolytes. If there are no electrolytes, there is no corrosion whatsoever. You don't have intragranular corrosion at all, no corrosion at all. Now, the question is, can a metal fail intragranularly? Can there be intragranular cracking can take place? Yeah, metal can undergo intragranular cracking. That is also called, that can happen in is a temper embeddlement, for example. Sometimes, if the metal is wrongly heat treated, right, there are some segregation of elements that go to the grain boundaries. And so it weakens the grain boundary. And as it weakens the grain boundary, then the metal becomes weaker. So when I apply a load, the crack preferentially travels through the grain boundaries intragranularly. That is not to be confused with intragranular corrosion, right? That should be seen as an improper heat treatment. And because of the load that is applied, because these are all precipitates the grain boundary, they cause the cracking along the grain boundaries. That is something like decohesion of grain boundaries taking place, and so there is going to be intragranular cracking. So it is should not be confused with intragranular corrosion. The intragranular corrosion comes because of chemical variation, that what you've seen in the case of sensitization. Okay, so they can be entirely different. For example, I can have a steel, a chrome, for example, a chromoly steel can have intragranular cracking. If it is, for example, it's called temper embrittlement, right? The temper embrittlement can lead to these problems actually. Sometimes the temper embrittlement can be compounded with hydrogen. For example, there is a corrosion takes place, hydrogen gets into the material, the intragranular cracking is now compounded by hydrogen. Okay, that is called intragranular hydrogen embrittlement takes place because of tempered one. So it can accelerate it. So that depends upon how we visualize this. Yeah, there's no need for electrolyte there. It is possible that corrosion, it's possible that hydrogen is entered into the material, maybe reformer. For example, sometimes we have reformer tubes, right? In a refinery, there are reformer tubes and there is hydrogen, high temperatures, then hydrogen penetrates into the material. And chromoly steels are used in reformer tubes, and especially if you're not going to use 5 chrome, right? 5 chrome, or you're going to use 5 chrome and above, they are resistant to temper embrittlement, so they don't undergo temper embrittlement. They also don't undergo failure due to hydrogen combined with temper embrittlement. So this will be seen more closely and should not be seen in isolation actually. I hope that really answers the questions. If not, please do let me know. We can clarify it further, whatever question, whatever clarification that you need to seek. Okay. Is it fine? Okay. Let me go to the next question. The next question is by Savant Tadepalli. Okay. If I immerse stainless steel in concentrated sulfuric acid, deaerate it, and scrap off the passive film on top of it, then will it undergo active dissolution or repassivate? What a nice question it is, right? So that's what I mean. You people now start looking at the fundamentals, right? That's what you've done, right? So it's very interesting question. Okay, very interesting question, and very profound question, I would say. I think, right? So that means you understood why stainless steel passivate, right? Why do the stainless steel passivate? The stainless steel passivate because the corrosion potential lies in the passive region, right? So I'm going to draw this diagram here. This is your so-called Evans diagram or a polarization diagram, right? I draw this. What's the E, right? This is towards positive direction potentials. This is towards a relatively negative direction of the potentials, right? Suppose if I look at the polarization curve of a stainless steel, it may be something like that. I'm just drawing a sketch like this. Okay. Now, assume that in sulfuric acid, this is the anodic reaction for the stainless steel. And if there is a cathodic reaction, assume that the cathodic reaction cuts something somewhere here. This is the corrosion rate. Corrosion potential, the corrosion current density. Am I right? This is the corrosion current density. And this is your E car. Now, if I'm going to aerate it, right? You are going to aerate it. Now, what happens? Now, possibly you may have oxygen there and you get something like this. The cathodic reaction takes place, right? This is the reaction due to, let's say in acid, you have oxygen plus 4H plus 4 electron gives me water here, right? And because as per mixed potential theory, the intersection occurs here, right? The metal becomes spontaneously passivating. Actually, it passes spontaneously. The metal is now passivating. Now the corrosion rate, the corrosion current density for this metal is equal to the passive current density. Am I right? This is what happens here. So that means the stainless steel requires the oxygen in order to passivate. Okay. That also depends upon the critical current density. For example, if the critical current density is smaller, for example, assume that there is a critical density very small here like this. Okay. Even there's a small amount of oxygen present, even the small amount of oxygen is present, the guy starts passivating, right? It's possible to happen. Now, coming back to the point that you've taken a vessel and you've taken the sulfuric acid, okay, and it is now kept here. It is exposed to air, and now it starts passivating. Now, what do? You want to do that? You want to close it now, and you are going to deaerate it now, right? You are going to bubble it now, right? You are going to bubble this with the nitrogen. Okay, there's also an exit, right? It goes here. The oxygen and plus nitrogen comes out of this actually. So over a time period, the oxygen content comes down. Now, as you said rightly, it is possible that the amount of oxygen required to maintain the passivation is very less. You don't need that much oxygen now because this guy is already gone here. So that means what happens? Even if the oxygen is very low, the passivation remains there actually, no problem. But now, if you make a scratch, what happens? You make a scratch, the bare metal is now exposed to the surfaces. That means I need more amount of oxygen in order to passivate again. Okay, so that is what it is. So that means I can passivate provided I have large amount of oxygen content. So that means how much oxygen content is required, that's a different story that one has to study. But it will undergo active dissolution unless otherwise there's sufficient amount of oxygen is present to repassivate again actually. So it's a very good question. It is very similar to what you do in nitric acid test. We can also do this kind of test actually. It's a fantastic question. Okay, I hope Savant Tadepalli is clear about this particular question or problem, right? There's another question by him again. It is why providing standalone corrosion protection is not a primary purpose of conversion coating. Very beautiful question, I think. Okay. Okay. Why is that we don't do that? So what is the conversion coating? First of all, the conversion coating, when we take let's take a metal, maybe a steel you take, right? This is steel surface, right? The steel surface here. Okay. Now what is the conversion coating? We're converting the surface into some form of oxides, maybe chromates, maybe phosphate. Essentially, it is not a metal anymore. It is a corrosion product, right? Corrosion product like your chromate, maybe phosphates, could be sometimes even a silicates can happen. Okay, so you form a thin layer of this is called conversion coatings. Right? Now, excuse me. Now, how does the conversion coating offer protection to corrosion? By a barrier action. There is oxide film here. This oxide film offers a barrier for the environment to enter the metal. How effective is a barrier? To compare this with the paint coating. Paint coating is a solid coating, right? A few micron, nice polymer film or maybe oxide film, whatever that you do that. That is a very, very solid coating. This case is a coating formed by the corrosion process. Please look at it. Is not like a stainless steel where you form a nice chromium oxide passive film, thin film. No, this is a corrosion product like iron phosphates, or sometimes you can change the phosphate into iron zinc phosphate, for example. Okay, you can do that, or the manganese phosphate. So the corrosion resistance of this particular metal depends upon how good is the conversion coating. The conversion coating is not that capable as you see in the case of a paint coating. This will for example, may dissolve. For example, you leave for a longer time, it may dissolve actually. It may slowly degrade. So what that means, suppose, for example, you take this conversion coating and put them in a salt spray test. Now we call salt fog test. Suppose salt fog test. How long it takes to get the red rest? You may get 300 hours, 400 hours, something like that. Suppose you apply a paint coating, it may take maybe 1,000 hours. Of course, depend upon the paints, right? So this is a coating primarily given in order to improve the adhesion behavior, adhesion performance of a paint coating. Suppose I give a faster coating and then apply a paint coating. Here, the paint coating adheres very nicely to this. The adherence is an important property for any paint coating. If it's not adhering, that's not going to be good at all. So the primary function of this is gives good adhesion. What is secondary function? Secondary function is even when, for example, corrosion liquid goes like this inside, okay, because the paint coatings are not 100% permeation free, right? So that time it really offers resistance for corrosion because that's going to be there. So that means these are not something, a fantastic thing. They are going to be good. But now there are also standalone coatings, conversion coating. What are standalone conversion coatings? The standalone conversion coatings are the manganese coatings, right? You have manganese added coating. In this case, you are also adding a manganese. You also put some kind of some epoxy resin. So they put epoxy resin plus manganate. They give you coating. The conversion coating is really good coating. It's a combination of conversion coating plus your epoxy. This is sometimes people call it a misnomer. They call as what they call as rust converter. They call rust converter. Rust does not convert into metal. The rust is converted into a coating actually, epoxy. So when you do a phosphate coating, the rust is converted into a phosphate coating along with a resin and gives you better performance. So you can have a standalone manganese, phosphate coating, hard manganese phosphate coating that gives you. Similarly, of course, anodizing is in a strict sense. I mean, in a scientific sense, you can call it as a what I would say as conversion coating, but people use a term reserved for that. It's called anodizing. But then aluminum oxide is very stable oxide, right? It gives you better actually. But even aluminum oxide, people use sealing. Unless there's a sealant, it won't really work very well. They use a sealant now actually. And there's one more similar thing called what you call as plasma electrolytic oxidation or micro oxidation. That gives you thick oxide coatings. That also gives you better performance because they're all thick coatings. But generally, normal conversion coatings are not good. So it won't give you longer life actually. Okay. I hope that point is clear to you. If you still have, please do type in your question so that I can answer you if you still have any questions persisting. Yeah, Samant has asked one more question. It is the question is like this: carbon steel has less corrosion in concentrated sulfuric acid compared to dilute sulfuric acid. Can you explain why? Is it because the additional oxygen reduction reaction, or will the above situation gets reversed in derate condition? Yeah, it's a very, very interesting question. I think I'm very, very happy to see that you're reading this, very well. Actually, these things. Let me just take this, yeah, this paper again one more time. Let me close this and. Okay, let me take this again. Please hold on for a moment. I will take this. word is a complicated one. I'll go to the again. Let me just give me a second. Yeah, probably I can write here better, I think. Okay. Yeah. So your question now is, I hope you are able to see. Okay. Your question is why, when the concentration of sulfuric acid is increasing at beyond certain level, the corrosion rate decreases. We also saw that similar thing in sodium chloride. I think your question is probably related to sodium chloride, right? When you talk about the sodium chloride, sodium chloride, right? When you had the concentration of NaCl, right? We talked about, right? And then versus the corrosion rate, excuse me, in water, we said that this goes something like that, right? And we said that the corrosion rate goes maximum here at 3.5% sodium chloride, because we said that when you add sodium chloride concentration, if you look at the oxygen solubility, it comes down, roughly. I'm not going to give a real things. This corresponds to this one. This is your oxygen solubility. Right. So that happens, right? The oxygen solubility decreases, and so what is the corrosion rate of what are the corrosion mechanism of steel in water? Iron, right? We consider this for simplicity as Fe 2 plus 2 electrons. Now this is now taken by oxygen here in a neutral water. Okay, this is the reaction, right? So the cathodic reaction in neutral water is predominantly oxygen there, right? The role of chloride is only to destroy the passive film, right? When you add here, for example, the corrosion rate increases because the passive film or oxide film formed on steel is destroyed by
Hello,
the
sir.
chlorides. Yeah, yes,
Excuse me, sir. What you're writing is not visible.
not visible.
No,
Oh,
sir.
oh, sorry. Okay, then I will go to the. Let me go to this. Just give me a minute. Good that he told me. Just give me a minute. Can you see this now? The screen?
Yes, sir. It's visible.
Okay, very nice. I think then I will repeat whatever I said. Take this. Okay. Yeah. Let me then, in that case, repeat what I said. See, this question has an origin from this particular problem. That is role of NaCl on corrosion of water. Am I right? This is what the probably this happens from here, because I have also shown there. This is also taken from, I think, from Fontana book, or maybe from Ulick book. I don't know, wherever. Now we see that the corrosion rate of steel in water against the NaCl concentration, suppose you put here, right? And you see this here, the corrosion rate of steel in water, it goes something like that. The maximum goes like this here. And this is related to the fact that the cathodic reaction here, or the reduction reaction here, is nothing but oxygen plus 4 electrons plus water gives you 4 hydroxide. Of course, the metal dissolution reaction is simple. It goes like this, right? So this is the cathodic reaction, right? But then this reaction is oxygen there. Now, when you're going to add sodium chloride to water, what happens to the solubility of sodium chloride in water? The water solubility, roughly speaking, again, as I told you earlier, it goes like that. That means when you increase the sodium chloride concentration, okay, now look at this. The cathodic reaction is oxygen there. It forms hydroxide. That facilitates passivation, right? If you see the Purve diagram, right, passivation, right? So this it facilitates the passivation. So, but then what happens? The chloride destroys the passivation. So that means when you start adding chlorides, because of loss of passivity, the corrosion rate increases. But then what happens? There is one more phenomenon that is happening. What is happening is that when you add chlorides, the oxygen is getting decreased. So removal of passive film improves corrosion, increases corrosion rate, but it also makes the oxygen availability very less. So the corrosion rate finally drops like this. There are two opposing factors, and so here the maximum corrosion rate is happening. Okay. Now this is what I think probably you have been talking about. Okay. Now what is happening when you're going to talk about sulfuric acid? The sulfuric acid is slightly different story. Now what is happening here? What is happening? For example, let's take sulfuric acid. What is the corrosion rate in sulfuric acid? Predominantly, again, same is there. The cathodic reaction is H plus will accept 2 electrons and give you hydrogen gas. Okay. Now this is the reaction happens because of an acid. Now how does this H plus come into picture? Let's take sulfuric acid. You take sulfuric acid, some chemistry is required here to know. You take sulfuric acid. Now sulfuric acid dissociates into H plus HSO4, 1 minus. HSO4, 1 minus will dissociate into H plus SO4, 2 minus. Please notice these H plus which are responsible for this reaction. That means the sulfuric acid has to dissociate into H plus in HSO4 or H plus into SO4, 2 minus. If they don't happen, then this won't happen. Okay. Now, so what happens when the sulfuric acid concentration is increasing? What happens now? How do you increase sulfuric acid concentration? You are increasing by bubbling. You take water, and to water you add SO3. And so you take this. What happens? It forms H2SO4. Please look at this. Higher concentration means you have more of this, and it forms this. That means it has less tendency to dissociate. When the water content becomes less, the dissociation of sulfuric acid becomes less. So that means beyond certain level, the sulfuric acid does not dissolve. So this is not available at all, first of all. The second thing that also happens in sulfuric acid is very interesting, is that it also forms an iron sulfate, a film which forms on the surface. Iron sulfate is not a very, very strong passive film, but forms a reasonable sulfate film on the surface. Both of them contribute to the corrosion of this. Again, very interestingly, when you're going to increase sulfuric acid concentration very high, this film is now soluble actually. Okay. Then again, corrosion rate is increasing now because it forms simply a complex of this. So anyway, the point I'm trying to say is that this dissociation of sulfuric acid is suppressed as you start increasing the sulfuric acid concentration, so the corrosion rate is decreasing. So the mechanism is different. That's why I always say that we need to understand what is happening in this case. I also given some example about temperatures. Again, temperature changes can also happen. So understanding the phenomena is very important to look at it actually. Okay, I hope that point is clear. The other question again by him, Savant, is steel immersed in 0.8 molar sulfuric acid exhibited corrosion potential of minus 0.75 volts and adding 2 inhibitors, the corrosion rate decreased. The corrosion potential of A is shifted to minus 0.8 volt and that of B shifted to minus 0.65 volt. I marked A, B as mixed inhibitor, but in the answer it is written as A, cathodic inhibitor, B as anodic inhibitor. Okay. Now, why does it happen now? That means you need to now draw what is called as Evans diagram. Please draw the Evans diagram, right? Suppose I take this, all things you have to start with Evans, because this Evans diagram, it talks about polarization of metals, right? That's what happens. Suppose let's take this, again, potential E versus log I. Suppose I take a metal, let me just take a metal, steel metal, immersion 0.8 molar sulfuric acid. Let's take this. I take this and I draw I just draw a device diagram, something like that. Right? This is the I car I have, and this is the E car that I get from here. Okay. Now, when adding an inhibitor, the corrosion rate decreases. That means the E car, don't worry, E car. Now the I car is reducing. I car goes down from here to this, right? How can the I car can come like this? The I car can come down to this value if, look at this, if this guy can go up like this. If this guy goes up like this, please look at what happened to E car value. The E car value moves from here to this. That means it is going towards a positive direction. That means this is relatively positive. Among these two, which is relatively positive? It is minus 0.65 volt is a positive, right? Right? So that means what kind of inhibitor it is? What does it do? This changes the slope from here to this. That means moving from here to this. It is affecting the anodic reaction. So it is called anodic inhibitor. Similarly, you can also look at, I can also reduce this cathodic reaction like this, right? Now what happens? Look at this. Corrosion rate is again decreased from here to this. But what happened to corrosion potential? The corrosion potential has increased from this point to this point here. Okay. So this is what really happens in this case. If it is a mixed potential, it is very interesting. Now, if it is mixed potential, what happens? Please draw. Suppose, assume that the inhibitor is both controls, reduces the anodic reaction, reduces the cathodic reaction, for example. See what happens? The potential almost does not change much. So E car does not change much. Actually. Of course, a slight shift can happen, but it won't happen so significantly. So the point here to be seen, I tell all the people, is the mother of the understanding of corrosion kinetics is the Evans diagram, the kinetics. You have to first resort to that. Go there and try to make the point, whatever you're making like this, okay? Try to make this diagram, right? When you start making this diagram, the answers come very well. And there is no ambiguity. It is not that Professor Raja is saying something or the TAs like Ranjit is saying something. No, you can able to see yourself what really happens. So Evans diagram is a very important one. Please do always follow the Evans diagram and try to construct it actually. And you'll never get a wrong answer. You never get, not just answer. See, its answer is only, what you talk about in the exams. I'm talking about you never get a wrong solution to the problem. Industry also don't get a wrong solution to the problem. So I would go beyond just the answer. You don't get a wrong solution to any corrosion problems. You must always start with the Evans diagram. And that's why the understanding of that is very, very important for us. Okay. I hope Savanth has a clarity now actually. Okay. Let me go to the next question. If there are no, if he doesn't seek any clarification, let me go to the next question. The next question is by Dr. Daulat Kumar Sharma. Okay. Very interesting question actually. Okay. How pitting tendency of a metal increases with increase in surface roughness. So it's a fantastic thing. This is one of the problems in the NPTEL. Although the NPTEL helps people to understand this kind of interaction. No, I said in online class, in offline class where you are face to face, you're seeing. I think you would be able to answer this clarification. This is a very interesting thing that happens, right? Now we must go to the basics now. Okay, what is this pitting tendency? Let's go to the basics. the basic that we go here is very simple. I'm going to now take this thing one more time. Please give me a minute. Okay, I will again go and just give me a minute. Anyway, I'll take this. Okay. Let me go to the screen now. Yeah. See, we need to try to connect it now. Okay. Pitting tendency is what? The ability of the film, okay, to resist the attack of the aggressive ions, be it a chloride or be it a bromide, iodide, or whatever be the case, actually, right? And we also said that pitting occurs only on the metals which are passivating. In a steel, we don't call it pitting in real sense of it. Of course, sometimes you call a pitting if the alloy is a bit more defective. What does it mean? Suppose there are inclusions are there, right? There are inclusions are present in the metal, and there is selective attack takes place because the inclusions are preferential attack. We don't call it pitting, but anyway, some people you can call it pitting also, no problem. We call sometimes selective attack, but you can also call it pitting because surrounding this inclusion, the pitting is preferentially happening. Now, so coming to the point in this case, if you go and understand what really happens in the pitting, okay, you will notice that there is a film damage. That means I have a metal which is passivated, the film is broken at different places. Why does this film break? The film breaks for two reasons. I think, okay, we have seen. One reason is you have an aggressive ion that takes place. The other reason could be the application of the potentials. I apply E, right? A potential E is applied. Of course, one more thing, if you want it, you can also call about temperatures. And you want to even add, you can call it pH also. Okay, these are also related to each other, right? Anyway, right? The pH is lowered, becomes acidic, pitting becomes more, right? It happens now. Let me look at this. Let's take the case like a chloride pitting. That means the stability of the film is very important. How does the film form? The film forms by the corrosion of the metal, and then the corrosion products spread on the surface and forms a film. I'm telling a very, very simplistic definition of passivation because that may not be the true things, but certainly it is one of the mechanisms of passivation. That means I have a metal surface, right? And I have forming a film on this actually. Cross section, right? It's a cross section I'm doing, right? Now, this film formation, the quality of the film depends upon the quality of the surface, right? If the surface is quite rough, all the things happens. Now, what happens? The film that is formed here may be weaker. They are weaker, and so you find that the film is preferentially destroyed whenever you have rough surfaces. So, if you're going to make the surface, let's say mirror-like finish, for example, the pitting resistance increasing because the film formation becomes quite compact, quite adherent, for example, and there's not going to be much of defects at all actually. So the surface roughness also means the film quality formed on the surface is not great enough. So that's a problem that you do it. In fact, it is one of the important way of selecting stainless steels. When you talk about selecting stainless steels, you say high chromium content, high molybdenum content, nitrogen content, all we do that. Oh, good. But if people don't take care of the surface, if surface, for example, somebody gives a 2B finish, okay, or somebody gives a rough finish, for example, you find that the pitting tendency of these stainless steels will change. That is the reason why industrially, when people select stainless steels, they mention the quality of the surface finish. The quality of surface finish also gives you a proper life of the material actually. So it is very important one. How will you see this? You can also carry out a polarization experiment. You can find out the pitting. For example, you can look at the pitting potentials. You see that pitting potential increases when the surface becomes smoother and smoother. When the surface becomes rougher and rougher, the pitting potential drops. When your roughness is increasing, okay, the pitting potential is dropping here. Okay, that is because the film quality is not good when surface is going to be rougher. I hope that point is made clear to you. Okay. Let me go to the next question. And next question is from Savanth Thadepalli. Very nice. Why cannot the cathodic reaction slope and anodic reaction slope both change at the same time? Because even then, ICAR will come down. That is the purpose of, that is what it is, right? I agree with you, right? That is the purpose of mixed inhibitor. Agreed, right? That is the, so that depends on what inhibitor it is. Okay. So what kind of inhibitor it is? If the inhibitor as can change the cathodic tablet slopes, anodic tablet slopes, then you can control the corrosion rate very much, right? Then it becomes a mixed inhibitor. Now the question is, can all the inhibitors be mixed inhibitors? No, not necessarily. Okay, because the absorption tendency of the inhibitor will depend upon what kind of molecule that you're going to have. Okay, for example, some inhibitor like amines, they preferentially absorb on the anodic surface, and so it is called as anodic inhibitors. Some inhibitor like, for example, zincate. No, so people add zincate in cooling water systems. Zinc, they absorb on the cathodic surface. The mechanisms are complex. Again, we don't have time. For example, people add zinc ions, right? People add sodium zincate, cooling water system. How does the zinc really work? At a cathode, if you take a cathodic metal, at a cathode, what happens? You find the cathode, there is oxygen reaction to hydroxide, right? Can happen. Or there can be a cathode, there can be elimination of H plus, can convert into hydrogen, right? In both the cases, the pH increases. So in a cathodic inhibitors, what it does is that they go and get precipitated here. What they do is when the pH content is larger, they get precipitated at the surfaces. So they become cathodic inhibitor. Okay, so it is depending upon the molecular structure, depending on the mechanism. An inhibitor can be anodic, it can be cathodic, it can be mixed also. Both are possible to do that. Your point is very well correct. Can it not happen? Yeah, it can happen. If it happens, then automatically, you see here, that's what you draw the diagram, right? If you draw a diagram, you will come to know what happens at all, right? In fact, in that case, both the you draw the diagram and see what happens, right? E versus this. Suppose I have a corrosion takes place. Assume that I have both inhibitors. See, the slope is going to be there. Okay, compare this. Okay, so it's not going to, okay, compare with this for same corrosion rate. Okay, if there is only one inhibitor, for example, if for example same corrosion rate, if it's only cathode inhibitor, what happens? Look at for this corrosion rate, this guy cannot help, right? This guy will have to be something like that, right? So you find inhibitor has to be very, very strong. This has to go only here. Suppose if it is only affecting cathodically, the potential cannot be this. It has to be lower than that. Okay, the point is correct. I mean, we are not saying that there cannot be mixed inhibitors, but if the mixed inhibitors, the shift in potential is not going to be significant. Okay, it's significant if it is going to be either anodic or cathodic. Yeah, it can be. Why it cannot? Okay, why it cannot be mixed inhibitor? That depends on the property of the material, right? That depends upon the property of the inhibitor. The inhibitor, because okay, how does the inhibitor really work? For example, what are the mechanism through which? Let's take a benzotriazole, for example. Assume that I'm going to use a benzo. And suppose I take an azole compound, right? Suppose I take like this nitrogen, right? It has got a pair of electrons, right? And these pair of electrons will get absorbed on the metal surface, right? Suppose I have a metal surface, right? This guy go and get absorbed to this. Now this will get absorbed when where the location is less in electron density, right? When there is electron density is more, it won't get absorbed actually, right? So preferably this guy gets absorbed because of this kind of thing, right? Okay, this gets absorbed because nitrogen has two lone pair of electrons, right? One lone pair of electrons. So this guy cannot go and absorb when there is more electron, wherever there is more rich in electrons. So this guy will go and absorb on the surface where the electron density is going to be lower, which is going to be an anodic inhibitor. Now that depends upon the molecular structure of the particular molecule talk about. You can have, for example, I can incorporate one more here, wherein I can have, for example, I may have a molecule where there is a positive charge located to this. Then I can go, it'll go and get absorbed here, no problem. Okay, so basically it depends upon the molecular structure, and so it can act as an anode, cathode, or you can synthesize a molecule which can be both anodic and cathodic. But in that case, they may not absorb so easily. See, again, there are a lot of issues here. For example, can every molecule absorb same manner? No, not necessarily. That is depends upon the free energy of absorption. It has to be more negative, right? So there are so many issues going to be there. It's not necessarily that just because I'm putting that it will happen. People also work. People are start working on density functional theories. They all there are people working on inhibitors. They understand the theory much better. They tailor it based on the first principles. First principle, what called density functional theory. They use it in order to get this molecule tailored at all actually. Okay, but it's a good question. Okay, no doubt about it. But I think I would have happy to answer it maybe a little more at different times so that we can understand the how the inhibitors are tailored, synthesized practically in this case, or how do you really understand it actually. So there are a lot of science behind in this kind of uh, synthesizing various kinds of inhibitors. I hope that I have answered you partly. Okay, so this is a science by itself as to how to synthesize. Not that all of them will get absorbed. For example, some inhibitor we say about 90% efficiency. It can reduce corrosion by 90%. Some of them only 45%. Okay. What has happened? Because the molecule has the ability to get absorbed or absorb on surfaces. For example, let's say I'm going to use benzotriazole called benzotriazole BTA or triazole, for example. Okay, they use it for copper alloys. These inhibitors form on the copper surface. You can see a very nice film, a thick film is formed on surfaces. This is called as film forming inhibitors. Okay, so the mechanism of corrosion inhibition depends upon the molecule, depends upon the metal. Of course, it also depends upon the environment actually. Okay, but for us, unless we understand them in more in detail, we cannot synthesize. We can't use them more properly. So instead of taking one molecule which is poorly mixed inhibitor, it's not a very good mixed inhibitor. Rather, I will take two molecules. One is a very good anodic inhibitor and very good cathodic inhibitor. I put them together, it works far better, right? Rather than taking a mixed inhibitor whose efficiency is not that great. So this is how the industry works, to 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 control the corrosion. Any other questions?
No, sir.
Okay. So it's very nice, you people, and it's very, very, I would say, a fantastic interaction. And please keep, going through this lectures, and you do write actually frequently whenever you have doubt. Very, it's important that we understand the basics, because corrosion is a very complex process. There are millions of environments, there are hundreds of alloys, there are different types of applications actually. Okay, it's very difficult to go and find a table, wherein you can get list of environment, list of metal, list of fabrication technique. You cannot find answer like that actually. The only way that you can find the answer is to understand the basics, fundamental, and they apply it to every problem that you encounter actually. And very unlikely you go wrong with any of this, solutions that you propose to that. Okay. So happy reading and corrosion things, and I wish you guys very success not only in the course and also in implementing the corrosion control. Okay, so if there are not any questions, we can close the meeting. Can you close the meeting? Okay, yeah. Okay, thank you so much. Yeah.